Now we go to the next level, which is knowing what the names of these different elements are. So chemistry has this really useful tool that's called the periodic table of elements. It's basically a table that shows all the elements we know of up till now. It's a little hard to memorize all of these, so I don't expect you to do that, but I want to show some of these right now because there's really no way of studying chemistry without memorizing the names of the elements. It's kind of like the letters in the alphabet. So if you don't know the letters, you really can't read a novel. The periodic table organizes all of these elements. So the first thing is you need to know that periods are what we call the rows in the periodic table. So everything horizontal here is a period. So this is period number 1 from the top, and then this is period number 2. So you can see those numbers are written here. The groups are the columns in the periodic table. So this is group number 1, group number 2, 3, 4, 5, all the way to 18. First thing I want you to learn is just the symbol of the element and the name. So H is hydrogen. So you can see here in larger text, H is hydrogen. Once you've seen this a few times, you'll get the hang of what elements is name what. So C is carbon. You can use a different periodic table than this if you want to help yourself study. You can use flashcards, and I would say memorize the first 4 period all the way to krypton, starting from hydrogen. So element 1 through 36. Okay. The periodic table is useful because it tells us a lot of things, and these are all things you want to know. One is the state of the elements that they're found in. So when I isolate oxygen, for example, what is the state of oxygen? Well, oxygen is a gas. We know it, it's around us, we breathe it. The way this particular periodic table is set up is it color codes the symbols according to the state of matter. So everything that's black is solid, everything that's blue is liquid, everything that's red is gas. So oxygen, as you can see here, is a gas. The thing that's a little confusing to beginning students is that when you find oxygen, it's not found as O, right? As we said earlier, it's actually found as O2 because 2 of the oxygen atoms are stuck together. But this just tells you about the element oxygen, okay? But when we're talking about the oxygen gas that we breathe, it's actually O2. It's found in that form. Now, some elements come in just one atom. So for example, like iron, if I were to draw iron, it would just be like one of these circles right here because that's how iron is made up of. You can see here that these are all the gases, all the red letters. The blue letters, which is the Br and the Hg here, those are the only 2 elemental liquids. And then we have a bunch of solids. Another thing that's really useful about this is to know which of these are metals and which of these are non-metals. Turns out that metals have certain properties. They can conduct electricity, they can conduct heat. Non-metals have different properties. Sometimes they're very reactive, like oxygen. It's not a metal, it's a gas that we can breathe. So all the metals are color coded. The box itself is color coded yellow, and then the non-metals are color coded green. And then there's these group of things that we probably wouldn't spend too much time talking about. They're called metalloids. They have properties that are in between the metal and non-metal. So some of them become really useful in certain applications, like silicone, for example. Si has properties that allows it to do really well in conducting electricity in those computer chips. Those are things that I want you to know. Be able to determine when you look at a periodic table like this, what's a period, what's the group, which ones are metal, non-metals, metalloids. Be able to know which ones are solid, liquid, and gas. Okay? And of course, the name and the symbol. You see this number here at the top left of each of the box? That actually is what we call the atomic number. That number tells us the number of protons. The atom is composed of protons, neutrons, and electrons. So the number of protons is what that top left number is. So for example, hydrogen has 1 proton. For something to be an atom, it has to have a neutral charge. The 2 subatomic particles have to have the same number because they have to balance each other out. That's one of these laws of nature, this electrostatic force, right? So if I have 4 protons here, I must have 4 electrons. So as a piece of information, this becomes really useful because if it tells us that hydrogen has 1 proton, then the hydrogen atom must also have 1 electron. Okay, so here's an example. How many protons and electrons are found in an atom of potassium, which has the symbol K, and chlorine, which has the symbol of Cl? So we can look up the periodic table, find K, which is right here, and look at that number. 19. That means 19 protons in potassium. If there's 19 protons, the potassium atom must also have 19 electrons. The next one is chlorine. Find that its Cl is right here. That's a non-metal. It has 17 protons, so it must also have 17 electrons for the atom. Okay, and I emphasize here the atom because, as you'll see later on in future chapters, we have other types of chemical species called ions, and ions don't have a equal number of protons and electrons. Right now we're just talking about atoms, so atoms always have the same number of electrons and protons. We're going to wrap up our discussion of the chemistry part of chapter 1 with the discussion about changes in matter. So really the reason we study chemistry is because we can take one thing and we can convert it into something else. So there's some terminologies we need to know, and this has to do with what we call properties. So a physical property is something that we can see of that sample of matter without really changing its chemical composition. So for example, water. If I give you a sample of water, what does it look like? It is clear. Below 0 degrees Celsius, it forms solid. We call it ice. If we go above 100 degrees Celsius, it becomes steam. We can do that when we heat up the water. We can, for example, put it on a scale and look at how much mass it has. Its density, which is something we'll talk about more later, is actually 1 grams per cubic centimeter. Does it conduct electricity? Not if it's pure, but it does conduct electricity if it has some other things that dissolve in that water. Here's another thing, right? Butter. What is the physical property? It's yellow. It is solid at room temperature. But then if you heat it up, it will melt, right? It becomes a liquid. And the melting point, which is the temperature at which it goes from solid to liquid, is different than water. So that's physical property, just properties we can observe with our eyes without doing anything in terms of changing the chemical composition. Now we can boil it, we can cool it down, transfer it from one container to another, but that doesn't change its chemical composition. A chemical property is the property that we observe of those substances when it undergoes what we call a chemical reaction. And chemical reaction is when you take that sample and you add something else to it that would cause it to turn into a different compound, a different molecule, a different atom. Iron is a good example. Iron, originally, when it's new, it's really shiny. But over time, if you let it be exposed to air and water, it will look like this. It will rust. So that rusting process, right, going from the shiny iron to the rusty iron, that's a chemical change. The ability of iron to rust is what we call a chemical property, because not every metal can rust. So for example, chromium doesn't rust. The right side here is chromium, which is why we use that to layer over some other metal to protect it from rusting. In fact, we might layer that over the iron. That would protect the iron from rusting when it's exposed to air and water. Okay. Other examples of chemical properties are flammability, which is how easy is it to burn it. Burning is a reaction with oxygen gas. So some things burn really well, some things don't burn much. Toxicity, if you eat it, does it kill you, right? And there's a reaction because when you take that compound in, it's going to react with another molecule in your cell, and that's what tells you whether it's toxic or not. With chemical and physical properties, we also have physical and chemical change. These are basically related terms. The physical change is a change in the state of the properties that doesn't affect its chemical composition. For example, when we melt that butter earlier from solid to a liquid, so you can see that it's changing, or the water here goes from liquid to steam, but it's still water. The molecule that makes up butter, which is fat, it just exists in the solid form versus a liquid form. However, with chemical change, this is when you actually change it. For example, like here's your water molecule, right? It's composed of oxygen and hydrogen. So if I run electricity through a sample of water in a process called electrolysis, I can actually take this thing and break it apart into hydrogen and oxygen gas. So now they don't look the same anymore. So that's what we call chemical changes, when you actually change the molecular identity or the atomic identity of that substance itself. Another name for chemical change, chemical reaction. This is a word you will hear a lot in chemistry. We would just say reaction. And anytime we say reaction, that means that we're taking something, another thing, and combining them together and converting them to something different in terms of their chemical formulas.